Today we're diving into one of the most fascinating phenomena in nanoscale thermodynamics, the surface-to-volume dominance paradox. This is where our classical understanding of stability gets completely flipped on its head. Let's start with a question. What is the classical view of stability in thermodynamics? In classical thermodynamics, we assume that the bulk free energy dominates. The stability of a system is determined primarily by minimizing the Gibbs free energy of the bulk material. The total Gibbs free energy is approximately equal to the bulk Gibbs free energy. This scales with the number of particles or volume of the system. Surface effects are treated as small corrections that we can often ignore. This works beautifully for macroscopic systems like a liter of water or a kilogram of metal. But here's where things get interesting. As we shrink a system, the mathematics of geometry creates a profound shift. Let's consider a spherical particle of radius r. We'll examine how volume and surface area scale with size. The volume is 4/3 pi r cubed, which scales as r cubed. The surface area is 4 pi r squared, which scales as r squared. Now here's the key insight. The ratio of surface area to volume scales as 1 over r. As the radius decreases, this ratio increases dramatically. For a sphere, A over V equals 3 divided by r. This simple equation contains the essence of the paradox. Now let's write the complete thermodynamic free energy, including surface contributions. The total Gibbs free energy equals the bulk Gibbs free energy plus the surface Gibbs free energy. More explicitly, G total equals N times Gm plus gamma times A, where N is the number of moles, Gm is the molar Gibbs energy, gamma is the surface tension, and A is the surface area. For a spherical particle, let's express this entirely in terms of the radius. G total equals 4/3 pi r cubed times rho times Gm plus 4 pi r squared times gamma, where rho is the number density. Now let's ask a critical question. At what size does the surface energy become comparable to the bulk energy? We set the bulk energy equal to the surface energy to find the crossover point. 4/3 pi r cubed rho Gm approximately equals 4 pi r squared gamma. Solving for r, we get r critical approximately equals 3 gamma divided by rho Gm. Let's calculate actual numbers for gold nanoparticles to see when this crossover happens. For gold, the surface tension gamma is approximately 1.5 joules per square meter. The density of gold is 19,300 kilograms per cubic meter. The molar mass is 197 grams per mole. The number density is 19,300 times 6.02 times 10 to the 23 divided by 0.197, which equals 5.9 times 10 to the 28 atoms per cubic meter. For the bulk free energy of formation, let's use minus 400 kilojoules per mole, which is minus 6.6 times 10 to the minus 19 joules per atom. Plugging in, R critical is approximately 3 times 1.5 divided by 5.9 times 10 to the 28 times 6.6 times 10 to the minus 19, which gives approximately 1.2 nanometers. Below approximately 2 nanometers radius, the surface energy becomes the dominant thermodynamic variable. This is the regime where the paradox emerges. Now let's explore the most dramatic consequence, how this reverses classical stability predictions. Classically, if a material has negative bulk free energy, smaller particles should be more stable because they minimize the total positive free energy contribution. However, surface energy is always positive. Creating new surface always costs energy because you're breaking bonds. Gamma is always greater than 0. This is a fundamental thermodynamic constraint. At the nanoscale, when surface dominates, smaller particles become less stable, not more stable. This completely reverses the classical prediction. Here's a graph showing the free energy versus particle size. The blue curve shows the classical regime where smaller means more stable. The red curve shows the nanoscale regime where the trend reverses due to surface dominance. One of the most important manifestations of this paradox is the Gibbs-Thomson effect, which explains why small droplets evaporate faster. Let me ask you a question. Why do small water droplets evaporate faster than large ones, even at the same temperature? The answer lies in surface curvature. The increased surface-to-volume ratio raises the chemical potential of molecules in small droplets. The Gibbs-Thomson equation is the natural log of P over P0 equals 2 gamma Vm divided by RRT, where P is the vapor pressure over the curved surface, P0 is the vapor pressure over a flat surface, Vm is the molar volume, and R is the radius of curvature. Let's calculate a numerical example for water at 25 degrees Celsius. The surface tension of water is 0.072 joules per square meter. The molar volume is 18 cubic centimeters per mole, which equals 1.8 times 10 to the minus 5 cubic meters per mole. For a droplet of radius 10 nanometers, the natural log of P over P0 equals 2 times 0.07, 2 times 1.8 times 10 to the minus 5 divided by 10 times 10 to the minus 9 times 8.314 times 298, which equals 0.104. Taking the exponential, P over P0 equals e to the 0.104, which equals 1.11. The vapor pressure is 11% higher than over a flat surface. This is why small droplets evaporate so much faster. This surface dominance paradox is the foundation of classical nucleation theory, which explains phase transitions. Consider forming a nucleus of liquid from a supersaturated vapor. There's a competition between bulk and surface energy. The change in Gibbs free energy is 4/3 pi r cubed delta G versus plus 4 pi r squared gamma, where delta GV is the bulk free energy change per unit volume. For a supersaturated vapor, the bulk term delta GV is negative, favoring nucleation. But the surface term is always positive, opposing nucleation. This creates an energy barrier. Small nuclei have high positive free energy due to surface dominance. There's a critical radius where the free energy reaches a maximum. To find the critical radius, we take the derivative of delta G with respect to R and set it equal to 0. The derivative is 4 pi r squared delta G versus plus 8 pi r gamma equals 0. Solving for R, we get R star equals negative 2 gamma divided by delta G versus. The negative sign on delta G versus makes this positive. Only nuclei larger than R star will grow spontaneously. Smaller nuclei dissolve back into the vapor. This is surface energy preventing nucleation. The activation energy barrier is delta G star equals 16 pi gamma cubed divided by 3 times delta G versus squared. Let me give you an intuitive analogy. Think about blowing up a balloon. When you first start blowing up a balloon, it's very hard. The rubber is stretched tight and resists expansion. But once the balloon gets bigger, it becomes easier to inflate. The same pressure produces more volume increase. This is exactly the surface-to-volume paradox in action. At small sizes, the surface tension dominates and resists expansion. At large sizes, the volume properties dominate. The small balloon on the left has high curvature and strong resistance. The large balloon on the right has low curvature and weaker resistance per unit volume. Here's another analogy from social dynamics. Think about starting a new community or club. When a group is very small, it's hard to maintain. Each person must contribute a lot of effort to keep the community alive. This is like surface energy. But in a large established community, the effort is shared among many people. The bulk properties of having many members make it stable. The members who interact with the outside world, the surface members, determine whether the group grows or shrinks. At small sizes, they dominate the dynamics. Let's discuss one of the most important practical applications, heterogeneous catalysis. Here's a question. Why are nanoparticle catalysts so much more effective than bulk materials? The answer is that surface atoms have dangling bonds and lower coordination numbers, making them much more reactive than bulk atoms. At the nanoscale, when we reach the surface-dominated regime, most of the atoms are surface atoms. The entire particle becomes essentially all active sites. For example, consider platinum nanoparticles used in fuel cells. A 2-nanometer platinum particle has approximately 50% of its atoms on the surface. But a 10-nanometer particle has only about 10% on the surface. This 5-fold difference in surface atom fraction translates directly into catalytic activity differences. Another dramatic manifestation of the surface dominance paradox is melting point depression in nanoparticles. Bulk gold melts at 1064 degrees Celsius. But 2 nanometer gold nanoparticles melt at approximately 500 degrees Celsius. That's a 564 degree reduction. This dramatic melting point depression occurs because the surface free energy destabilizes the solid phase more than the liquid phase. The melting point as a function of radius is Tm of r equals Tm infinity times the quantity 1 minus alpha over r, where alpha is a material constant related to surface energies. Alpha equals 2 gamma SL divided by rho delta HF, where gamma SL is the solid-liquid interfacial energy, rho is the density, and delta HF is the latent heat of fusion. For gold, alpha is approximately 1 nanometer, which is why we see such dramatic melting point changes at the 2 nanometer scale. The surface dominance paradox also manifests in quantum dots, semiconductor nanoparticles with size-dependent optical properties. Classically, we'd expect the electronic band gap to be an intrinsic bulk property, independent of particle size. But in reality, when particles become smaller than the exciton Bohr radius, quantum confinement dominates. The band gap as a function of radius is Eg of r equals Eg infinity plus h bar squared, pi squared, divided by 2r squared times the quantity 1 over me star plus 1 over mh star, where me star and mh star are the effective masses of electrons and holes. As the radius decreases, the band gap increases as 1 over r squared. This is quantum confinement, a manifestation of surface boundary conditions dominating. Let's address a fundamental question. At what point does thermodynamics itself break down? Thermodynamics is fundamentally a statistical theory that assumes large numbers of particles and well-defined temperature and pressure. For particles with fewer than approximately 100 atoms, thermal fluctuations become comparable to average properties, and the concept of temperature becomes fuzzy. This corresponds to roughly 1 to 2 nanometers for most materials, which is precisely where we calculated the surface crossover occurs. Below this scale, we must abandon thermodynamics entirely and use full quantum mechanical descriptions. Let's discuss the profound implications for materials design and nanotechnology. In the nanoscale regime, surface engineering becomes more important than bulk composition. Coating, passivation, and surface functionalization dominate material properties. Nanoparticle stability requires surface stabilization through ligands, surfactants, or oxide shells to counteract the destabilizing surface energy. Many self-assembly processes are driven by the system's attempt to minimize total surface area, leading to structures like micelles and vesicles. Precise size control in nanoparticle synthesis is critical because properties change dramatically over just a few nanometers due to surface dominance. This diagram summarizes the two regimes. On the left is the bulk regime with size-independent properties and volume dominance. On the right is the nanoscale regime with size-dependent properties and surface dominance. There's a beautiful mathematical structure underlying this paradox. At its core, this is a problem of dimensional analysis. Energy is extensive and scales with volume, but surfaces scale differently. Bulk energy has units of joules, which is energy per volume times volume, giving length cube dependence. Surface energy also has units of joules, but it's energy per area times area, giving length square dependence. The ratio of surface to bulk energy scales as length to the -1. This divergence as length approaches 0 is the mathematical essence of the paradox. There's an interesting connection to fractal geometry that illuminates this further. Fractal surfaces have a dimension between 2 and 3. As we approach molecular scales, surfaces become increasingly rough and fractal-like. This increases the effective surface area even more than smooth geometry predicts, making surface effects even more dominant. Nanoparticle aggregates often show fractal scaling, where the surface-to-volume ratio scales with a non-integer power, leading to even more complex thermodynamics. This paradox is absolutely fundamental to biological systems, which operate at the nanoscale. Proteins, typically 2 to 10 nanometers in size, are firmly in the surface-dominated regime. Their function is almost entirely determined by surface properties. The hydrophobic effect, which drives protein folding, is fundamentally about minimizing water surface area in contact with nonpolar groups. Biological membrane formation is driven by the system attempting to minimize the unfavorable surface area between hydrocarbon tails and water. Viruses, at 20 to 300 nanometers, exploit surface-dominated thermodynamics for their assembly and stability. How do we experimentally verify this surface dominance paradox? One approach is calorimetry of size-selected nanoparticles, measuring their heat of formation as a function of size. Vapor pressure measurements verify the Gibbs-Thomson equation and demonstrate enhanced vapor pressure over curved surfaces. Transmission electron microscopy allows direct observation of melting point depression in individual nanoparticles. The size-dependent optical properties of quantum dots provide clear spectroscopic evidence of surface and confinement effects. Finally, let's consider the deeper philosophical implications of this paradox. This paradox challenges naive reductionism. You cannot understand nanoscale systems by simply scaling down bulk equations. It demonstrates emergence. Genuinely new physics appears at different length scales that cannot be trivially predicted from knowledge at other scales. Scale dependence is not a complication to be eliminated, but a fundamental feature of how nature works across hierarchies of organization. Let me summarize the key points of the surface-to-volume dominance paradox. Surface energy scales as r squared, while bulk energy scales as r cubed. Their ratio diverges as 1 over r. The critical crossover occurs at approximately 1 to 2 nanometers for most materials, where surface and bulk contributions become comparable. Below this crossover, classical bulk thermodynamics fails and stability predictions reverse. This manifests in phenomena like melting point depression, enhanced vapor pressure, nucleation barriers, and size-dependent catalytic activity. Understanding this paradox is fundamental to nanotechnology design and to understanding how biological systems function at molecular scales. Practical application requires careful surface engineering to stabilize nanoparticles against the destabilizing effects of high surface energy.